All right, so now that we've taken a look at the valence electrons, in this module, I want to examine the periodic table. So first of all, how do we read the information given to us in the periodic table? So the classification of elements in this periodic table is based on that electron configuration, which is why I wanted to go through configurations. We have 7 horizontal rows, which we call periods, and then elements in a column. These columns are known as groups, and they have similar valence structures. So not the exact same numbers, but the same types in that valence state. And then each entry contains a lot of atomic information that can be useful as we go through work with the elements. So this is an example of one of those entries for selenium. So selenium up here, and I want to point out here that this configuration is not universal. You may see slight differences, but up here in this version, the top left gives us the atomic number. So it'll be a whole number. That's its atomic number Z. You see the designation for selenium, so it's 2-letter abbreviation or 1 letter in some cases. Sometimes it will be spelled out, other times it won't, but here it's actually spelled out. Over here, you see the electron occupancy, and so these are of the various shells. And so this isn't as common to all periodic tables, but some of them you will see electron occupancy. And then down here at the bottom, this is one that's very common, is the atomic weight. And so again, keep in mind that the weight here is a weighted average of the various isotopes found naturally. And so this will almost never be a round number because it's this isotope average. And so atomic number, you will see an integer. Here you will not because of the averaging that happens. Okay, so this is an example of a periodic table showing that organization that we just talked about. But the main thing I want to stress here is that the organization follows naturally with those quantum numbers that we talked about. So the first row or period, is n equal 1. And then the next row, period, is n equal 2, 3, 4, 5. So the periods refer to the various principal quantum numbers in the first quantum number. And then after that, the designations of the columns here tell you about the azumnal or subshell quantum number L. So L equals 0 is what we would term S, right? And so that refers to these two groups. And then over here, we kind of skip the middle, and I'll tell you about that in a second. In the middle, over here, these refer to L equal 1, which is the p orbital, p subshell. And so that has 6, so you can see that's why there's 6 elements across. And then in the middle here, transition is where you have L equal 2. So these are the transition metals, and they refer to the d orbital. And so that's, again, why it is a certain width to it. And so d can have up to 10. And then 3 is down here with the lanthanides and actinides, and those actually fall into this space down here. And so those are referred to L equal 3 or the F subshell. And so that can have 14, which is why it's much longer than the others. And so that organization follows naturally from the principal quantum number and the azumnal quantum number. And that gives us the organization and the structure of the elements in the periodic table. So this was, put together without that knowledge of quantum numbers, but once we knew that, it made a lot more sense in terms of the structure of the periodic table. Okay, so like I mentioned at the beginning here, is that columns or groups have similar valence structures. And therefore, if they have similar valence structures, they're going to bond in similar ways. So I showed you this one before where this column or group refers to the inert gases. So they tend to be inert and not interact with others. And so they tend to be fine on their own. Whereas others, like this column or group with fluorine, they have a similar valence structure in that they will accept one electron to get to the configuration on the right here. So fluorine adds one, it becomes the configuration of neon. Chlorine adds one, and it's argon, and vice versa, all through these two. And so they all have similar structures. So all of this column wants to add one electron. All of these want to add two, and etc. Same thing over here. All of these, hydrogen wants to give up one electron. Lithium wants to give up one electron to get to neon. And the same thing for all of these. And so they all have similar structures. So these will all act similarly. These will all act similarly. Same thing here, same thing here, same thing here. And so the ones over here, which give up electrons very easily, are termed electropositive elements because they readily give up electrons to become positive. And then over here, these want to accept electrons, so they're electronegative because they readily acquire electrons, becoming negative ions. All right, so let's work on a little example here that will be in the quiz for this week, and that is list the valence electrons of oxygen. So use the periodic table, use the electron configuration method that we talked about, but then come up with which ones are valence. And then what oxidation state, so that means how many electrons and what charge, will result in a filled valence shell. So taking oxygen to its nearest noble gas configuration, what does that mean in terms of how many electrons were added or removed, and what is the charge there? And so then after that, you can write the formula of the oxygen ion. So if some of this doesn't sound familiar, do the best you can, and then come back and we will take a look at these answers. So pause the video, go to the quiz, finish that up, and come back, and we will discuss the results. All right, so we're back, and let's go ahead and look at these results. So with oxygen, and if we go back to the periodic table real quick, you see that oxygen has an atomic number of 8. So we're going to have 8 electrons. And so if we do that, we have all of the interior ones for the 1s. So 1s2, and 2s2, and then 2p4. That gives us to 8. So the valence ones are the outermost electrons, and so that's the n equal 2 shell. And so that means 2s2 and 2p4. So that means we have 6 valence electrons. And if you look at this configuration, this is partially filled. To be full, we would either have to add 2p electrons to get to 2s6, and that would fill the n equal 2 shell, or we could remove 6. So either add 2 or remove 6. As you're going to imagine, adding 2 is much easier. So if you do that, then the oxidation state is termed -2, right? Because we're adding 2 electrons. Those are negatively charged. And so what we term the oxidation state is -2 when it's in the noble gas configuration. And if we go back, so again, it accepts 2. So if we accept 2, we're hopping over here. And so it effectively has it goes from 8 to 10 electrons. So it has a configuration the same as neon. And so that's what we're doing here. And so when we write it as a formula for the oxygen ion, we write it as oxygen. So it's chemical formula. And then the superscript here is the oxidation state. So in this case, -2 or 2-. Sometimes it's written slightly different. If we had something where we removed 2 electrons, then it would be a +2. and then this would be a +2 down here. So that's what we're referring to with writing these formulas.